What we want is we want to divide vertices into two parts so that we have as many edges between the parts as possible. Well, again, we can state this as minimizing this function. So again, for every edge, we have this valued constraint. So f bar cut, actually it's 1 minus f cut, because here what we want is we pay 1 every time something is uncut. And we pay 0 every time an edge is cut. So when we minimize this sum, it's the same as minimizing the number of those guys, which is the same as saying we want to maximize the number of those guys. So this is why max cut is the same as min uncut. So maximizing the number of edges in the cut is the same as minimizing the number of edges that are uncut, and that's VCSP for this single function. So again, the blue edges here are the edges that are penalized, that cost something. The black edges cost nothing, the blue edges cost money. So these are specific problems that are VCSPs. Now, if we are looking again for an algebraic reason for some VCSPs to be tractable, solvable exactly in polynomial time, then we need to generalize this notion of polymorphism. And this is generalized in the following way. So we need a more flexible way than polymorphisms. So this is how it's done. Now, for a cost function, we can also consider polymorphisms, but normal polymorphisms that they are defined for a relation. Right? You have a relation, and a polymorphism is just a way to combine elements in this relation. But then with any cost function f, we can associate a relation that consists simply of all tuples on which f takes a finite value. So you simply exclude all the tuples that are entirely forbidden. And then we can say that a polymorphism of f is a polymorphism of feasibility of f. So basically what's a polymorphism of f? It's a way to combine it's a way to combine feasible solutions. So we don't say anything about how the cost is affected, but what we want is that if we take a bunch of feasible solutions and apply our polymorphism component-wise, what we get is a feasible solution. Right? We're not saying anything about the cost. Now the cost comes later in this definition of fractional polymorphism. So let me go through it slowly. Now it looks a bit ugly. In fact, it's not. And I'll give you a specific example that it will be clear. Don't worry. What's an Emery fractional polymorphism of f? Well, a fractional, like anything fractional, is a probability distribution on the things. So fractional polymorphism is a probability distribution on Emery polymorphisms of f, which in addition satisfies the following condition. If you take m feasible tuples for f, so m tuples on which f takes some finite value, and you take the average value of f on those tuples. So this is one quantity that you look at, and then you compute another quantity from these tuples, and that's how you obtain it. So omega is a probability distribution on Emery polymorphisms. So you draw a polymorphism G from this distribution. You apply this polymorphism to these tuples in the usual way. Right? You have m tuples here. You apply your polymorphism component-wise. You get again a feasible tuple. It has some cost. That's the cost. So this is what we do here. When we start with our m tuples and the average value of f on those tuples, then we draw a polymorphism from our distribution omega, apply it to these m tuples, look at the value. So the expected value must be not worse than the average one, than this one. And since we minimize, and not worse, means less than or equal to. That's what it says. So if you take m feasible tuples, then and you look at the average value of f of those tuples, it should not get worse after you apply a random polymorphism G drawn from the distribution of it. That's what it says. We will call such omega cyclic if all polymorphisms that get positive probability in this distribution are cyclic. A cyclic polymorphism is just one operation, that is a polymorphism, and is cyclic. So satisfies the cyclic identity. And here, what we say is we have a distribution on operations that are polymorphisms and that are cyclic. That's what we say. So all operations in support of omega are cyclic. That's what we have for a cyclic fractional polymorphism. Now let me give a specific example of a fractional polymorphism. Hopefully it will clarify some things. The modularity. You probably all heard of the modularity. It's a very important property that appears all over combinatorics, all over optimization. Well, if you haven't, that's the definition. A function defined on the subsets of some set X is called some modulo if it satisfies this inequality. If you take two subsets, Y and Z in X, and you add up the values that f takes on them, then this should be improved. That is, this should be greater than or equal to the sum of two values that f takes on the union and the intersection. So this is the inequality that defines some modular functions. And it's very, very important. So people who prove important things about some modular functions get best prizes in the mathematical optimization community. Somehow, yeah. Okay. Now, let me relate this to fractional polymorphisms. So if our set X here has m elements, then we can just view 2 to the power of X simply as the nth power of 0 and 1, right? So subsets in X are just n tuples of 0s and 1s. Okay. Now we see that f is submodular, satisfies this inequality, if and only if it has a binary fractional polymorphism omega that assigns probability 1/2 to max and to min. And max and min are the ordinary maximum minimum operations on 0 and 1. Well, let's write down what it means that f has this fractional polymorphism. On the right hand side we have so x1 and x2 here are 2n tuples of 0s and 1s, which clearly corresponds to these two subsets. And we take the average of them here. What do we have on the left hand side of the inequality? So we have the expected value that we get by drawing an operation from this distribution and applying it to x1 and x2. Well, that's the expected value. With probability 1/2 we get max. So here we apply max to x1 and x2 and compute f on that. And with probability 1/2 we get mean. So here we apply mean to x1 and x2 and compute f on that. So this is the average. This is the expected value. Now, of course, 1/2 can be cancelled in both parts, and what we have is exactly this, right? Maximum on 2 Boolean tuples corresponds to the union of the sets. Minimum of 2 tuples corresponds to the intersection of sets. Hopefully, this much is clear. And if we try to look at our functions that we had here, f cut and f bar cut here, then we can see that f cut is modular. Well, this can be just checked by you just go for various different pairs of x1, x2 and check. And this function of bar cut is not submodular. Well, if you just take these two pairs, so this is x1, this is x2, the average value is clearly 0. But if you take that distribution, well, it gives weight 1/2 to minimum, 1/2 to maximum. But whatever you choose, minimum or maximum, of these two tuples, you will get this or that. So after you draw an operation G from your probability distribution and apply to these two tuples, you are on this side. So the expected value will be 1, regardless of what you draw, minimum or maximum. So see, the average value was 0. After you apply the operation, the expected value is 1. So it got worse, which means that this function is not submodular. So and here we have the difference. This was a tractable problem. This is an intractable problem. And we already found some kind of algebraic condition why one is one and the other is the other. Okay, again, like in the situation with 3SAT and 2SAT and 3SAT, let's try to make it more general, and we can. There's this recent conjecture made by Krokhin and Vladimir this year. If we have a rigid core gamma that has a cyclic fractional polymorphism, then VCSP of gamma is tractable. In all other cases, it's in B part. So this sounds just like the conjecture for CSPs. The only difference is that we have fractional here and V here. And indeed, if we restrict this conjecture to CSPs, that is to languages gamma, where every function takes only value 0 and infinity, then we get the original theory conjecture. Again, the hardest part in this conjecture is a theorem. It's proved similarly to the CSP case. Actually, it appears in the same paper by Krokhin and Vladimir. This conjecture was confirmed in several special cases earlier, and actually there are many papers that sort of went in this direction. Each of these papers generalizes a whole bunch of earlier papers. So it's kind of its tip of the iceberg. I don't show you the iceberg because it doesn't matter. So these special cases that were confirmed when A is just 0, 1. It's an old paper by Kolmogorov, Jones, and myself. The case when gamma is finite valued was entirely settled by Tapper and Gigli, which was a really big surprise at the time when it appeared, because we have somehow, if you look at VCSP, it's a combination of CSP and finite valued CSP, right? Only feasibility issue, only optimization issue. So we know how difficult it is to settle the feasibility part, the CSP conjecture. And the optimization part, which corresponds to finite value CSP, was settled within a couple of years. That was a major, major surprise. Now, the case when gamma contains all 0, 1 valued unary functions, the so-called conservative VCSPs, was settled by Kolmogorov and Zhivny, and finally a recent result by Tapper and Zhivny says that if you can solve the feasibility problem associated with your CSP by a specific algorithm based on established local consistency, then this conjecture also holds. So you see, if you have a VCSP, before sort of going for optimization, you can solve the intermediate problem, the feasibility problem. You have an instance, is there a feasible solution to this instance at all? So before you start optimizing the value, you need to find out whether your instance has a feasible solution at all. And what is this feasibility problem? Well, it's nothing else but this. You take every function in gamma and you ignore the values, the finite values. So make all the finite values zeros. And then what you have is a CSP, which corresponds precisely to the feasibility question for your VCSP. So if the feasibility question can be solved in a specific way, then this conjecture also holds. That's the recent result by Durham and G. And here's the main result, which is the main result of this talk and this work with Kolmogorov and Rolinek. Here's what it says. Again, let's assume we have a rigid core. By the way, somehow I never mentioned this. This assumption of having rigid core, which I have in all conjectures and theorems, can be made without also generality. From an arbitrary gamma, we can always move to a rigid core for free. It's not entirely obvious, but it's an easy result. So assume we have a rigid core, and assume we have our VCSP of gamma. So, sorry, our gamma satisfies the following two conditions. The first condition says that gamma has a cyclic fractional polymorphism of some origin. And the second condition says that the feasibility problem associated with your VCSP of gamma is tractable. So you can solve the feasibility problem. If these two conditions hold, then your VCSP of gamma is indeed tractable. So basically, if you can find a feasible solution in polynomial time and you satisfy this, then you also can find an optimal solution in polynomial time. Which sounds very unusual, because feasibility and optimization are kind of two different problems. And in all other cases, VCSP of gamma is not tractable. So let me make some remarks on this result. Well, first of all, the necessity of these two conditions is clear. If you want your VCSP of gamma to be tractable, then you need to have this condition. That's by the previous. That's by Krokhin and Rolinek. This is what they proved. If you don't have that, then you're hard. The necessity of this is obvious, right? Because if you want your optimization problem to be tractable, then your feasibility problem should certainly be tractable. If you say I can find the best solution for polynomial time, then you can certainly find some solution for polynomial time. Right. So this theorem generalizes all the earlier results about the complexity of VCSPs. So everything that I showed here, for example, follows from this theorem. And in a way, it reduces VCSPs to CSPs. So basically, now once we know which CSPs are tractable, which are not, we will have a classification for all VCSPs. And in this sense, this was a very unexpected result, because VCSP seems to be such a general problem, much more general than just CSPs. You need to even be able to solve feasibility first, and then to do something about optimization. Somehow you need to do a lot. And it turns out that once you can do feasibility, then for this condition you can optimize. So that was very unexpected. Right. Then again, if the algebraic CSP dichotomy conjecture holds, the one that I showed you before, then this condition 2 is not needed, because it would follow from the previous one. And then, you would want to know perhaps how difficult is it to decide whether given gamma satisfies this condition. And for a fixed set A, this can be checked in polynomial time. So if you fix your set A, then you can take any gamma of this set, give it to me, and I can tell you in polynomial time whether this gamma satisfies this condition or not. Right. So what's the algorithm? The algorithm is based on the basic LP relaxation for VCSPs. And actually this is an algorithm that solves all finite valued VCSPs. And this is how it goes. Oops. So if you have, first you take your instance of VCSP of gamma, and you reformulate it in terms of integer programming. So you take some variables. This variable, the 0, 1 variable, that says that whether variable v is assigned variable a, and for every constraint you also have such a variable, and for every constraint c and every possible tuple t that you can assign to variables in this constraint. you have a 0, 1 variable that says that t is assigned to x. That's the idea. And then you have natural constraints saying that every variable is assigned exactly one label. That's what it says. You have consistency of modulos condition, which says that if you assign to tuple x, you assign tuple variables x, you assign some tuple of labels t, then this is consistent to what you assign to individual variables. Finally, you have a condition that says that you never assign anything positive to infeasible tuples. And this is just says, well, for every constraint you want to minimize this, and that's just it just says that's the value that you get by assigning some tuple to the variables in a constraint. Yeah, well, this is a bit vague. I admit what I just said. So this is just an IP formulation of a VCSP instance, nothing else. And you can turn this IP formulation into a LP relaxation if now you don't say that each of these guys is 0, either 0 or 1, but you say that they take values in the interval between 0 and 1. So basically, each of these PV and PC is a probability distribution. And then what it says is that it says minimize the expected value. That's what it says. Right. I don't think I have time to give you an example of this. Right. So this algorithm BLP it gives you some lower bound to its optimum. If you start from an instance, it has some optimum. You make an IP formulation. The optimum is still the same, of course, because you just reformulated the instance. When you make LP relaxation, you minimize over a larger set of possible solutions, so the optimum can go down. Sometimes it goes down, sometimes it doesn't. Sometimes it stays the same. In this case, we say that the LP is integral. So if there is an optimal solution that is integral. So this means that BLP computes the true optimum for your original VCSP instance. And in fact, VCSPs for which BLP, this linear programming relaxation, always computes the true optimum that have been characterized in a certain way. I don't think you have the time to go through the exact statement, but anyhow. And this is the tractability part of the main results. Remember, the main result, it says that some problems are tractable, the rest are hard. And the hardness was kind of easy. But here's the tractability part. Here's the algorithm for tractable problems. This is how it works. You have an instance. Now, for each individual variable, you compute infeasible values. So you have your instance, there's some variable v in it, and you try whether v can be assigned a in some feasible solution, which you can do. You just take your instance, add the constraint that says v is equal to a, and solve this as a CSP. If this new instance has a solution, then v can take value a in some feasible solution, otherwise it cannot. So in this way, we compute all infeasible values for individual variables. So infeasible means that this variable cannot take this value in any feasible solution. So we compute those by using this assumed algorithm for CSP. And this is possible since we come with rigid core and we can always fix values of variables. Now, once we compute the infeasible values, we add this information to the instance. So for every variable, we add the unary constraint that explicitly forbids infeasible values. And after that, we simply run BLP, this basically a programming relaxation, on the obtained instance. And finally enough, it always gives you the correct value. So in the first step, or in fact the first two steps, we clearly never ruled out any feasible solution. Right? So since no feasible solution disappeared here, if we get an optimal solution here, that's the optimal solution for the original instance. So the algorithm is very simple. First, run your algorithm for the feasibility problem to explicitly rule out infeasible values for individual variables, and after that, run your linear program. And that's it. And of course, the bulk of the paper consists in proving that this algorithm is actually correct. It always gives you the right result. And I think here I need to, Here I need to stop. Let me just summarize what I told you. I told you something about the tractability thesis, is that tractable problems tend to have some kind of algebraic structure and solution sets. And I illustrated it by convexity for optimization and for constraint satisfaction problems by polymorphisms, which are ways to combine solutions. You take several solutions, you combine them in a trivial way to create a new solution. And we discussed the algebraic CSP dichotomy conjecture, which is stated in terms of polymorphisms. It says, if your CSP has an algebraic, non-trivial algebraic structure, then the problem is tractable. The lack of algebraic structure means the problem is hard. Then we discussed valued CSPs, and a similar role to polymorphisms for CSPs is played by fractional polymorphisms. And again, we produced a classification of tractable VCSPs, modulo tractable CSPs. So basically, the classification question for VCSPs is now closed. It's all within CSPs. That's the bottom line of the result of the talk. Thank you.
Do you have any questions for Andrei? Questions, comments, counter-examples? Did I understand from one of those slides that it's determining whether you have a cyclic polymorphism and polynomial design?
Yes, if your set A is fixed. Because if your set A is fixed,
I see. Okay.
then there is a cyclic polymorphism of
fixed average.
some fixed arity, and you just go through all operations of this arity and check.
Yeah, I see. The more interesting question is still open, actually, isn't it? The complexity of determining whether the structure has a cyclic polymorphism at all, if the structure is infinite. So this is a meta problem, modulo the algebraic complexity.
Oh, that is a solve.
It's what? It's a
solve.
It's NP.
No, it's another thing.
To determine whether any input the structure determine whether it has a cyclic polymorphism. Any further questions? Well, thanks very much, Andrei.
Thank you. Since I'm the last speaker of this meeting, let us thank the organizers, Barney, Rajan, Giuseppe.
And finally, we would like very much to thank you all for attending and for staying for the last talk. Hope to see many of you at BCTCS next year in Northern Ireland.
Thank you for coming, and the sum of